Hello, my name is Dylan Tran, and I will be presenting an experiment from my structural analysis laboratory based on the tensile behavior of bolted connections with varying configurations. So, bolted connections are a fundamental element of structures. They're used to connect structural elements and transfer load between them. There are various factors that affect the performance of bolted connections, including the size of the bolts, spacing between them, their grade, and the number of bolts used. The objective for this experiment was to choose one of those variables. We decided to choose how the variations in the bolt spacing and arrangement affected the tensile behavior of the connection. So for this experiment, we gathered two sets of these paddle-shaped steel plates. We split them in half and overlapped them to create this 5-inch by 5-inch connection. We went with 5/16 inch diameter bolts with a grade of A307. And as a group, we came up with two configurations. The first configuration was standard. It had uniform spacing between the bolts and an edge distance of about 1 inch. The irregular configuration had a really small edge distance. We push the bolts really close to the edge at about half an inch in hopes of inducing a tear out failure. So here's our test setup. There's a transfer girder bolted to the foundation. And then we bolted our two connection plates to two plates connected to the transfer girder. And here's our connection zone in the middle. This was all set up with an actuator to apply the load. And the actuator came equipped with an LVDT to measure the displacement in inches, while the load cell measured the force in kips. So once we gathered all this data, we plotted it on a graph of load versus displacement. And during the experiment, our goal was to observe the failure mode, the deformation behavior, and the difference between the two configurations. So here's our results. We see the standard configuration in orange and the irregular configuration in blue. While the standard configuration reached a higher max load as expected, it was actually pretty close to the max load of the irregular configuration. However, where the two configurations deviated was the displacement. The displacement axis at the bottom is a measure of like the stretchiness of the connection. So we could see that the standard configuration stretched more, which makes sense because it was meant to be stronger. So the standard configuration reached a maximum displacement of about 1.57 inches, while the irregular configuration only stretched about 1.02 inches. These figures represent the failure planes in more detail. On the left side for our irregular configuration, we actually had a fracture failure instead of a tear out failure. We deduced that if we had used less bolts, we probably could have gotten that tear out failure because there would have been more force per bolt. Once we removed the washers and bolts, we actually observed that the bolt holes had been elongated, likely as a result from the bearing stress. We also observed these bumpy deformations on the edge of the plates from the bolts nearly being ready to tear out. For the standard configuration, we observed a staggered rupture failure, and we also observed a little bit of necking of the steel. We had initially expected that the standard configuration would have just failed from yielding of the steel from necking because the configuration would have been so strong that it would have been the steel yielding. Once we removed the nuts and washers, we also observed elongated holes from the bearing stress. In conclusion, there are a number of variables that affect the performance of a bolted connection, including the number of bolts, the bolt size, the bolt grade, and as we tested, the arrangement or spacing. We found that the smaller the edge distance, the lower the deformation capacity. And we also found that a uniform arrangement results in a small increase in strength, but a significant increase in deformation capacity. That's all I have. Thank you for listening.